talk about bond energy. Now remember, for ionic bonds, there were two ways to determine how strong an ionic bond was, according to Coulomb's law. We would look at their charge and the distance between the center of the ions. For covalent bonds, we have a little bit different set of parameters to think about in terms of their bond energy. So for a covalent bond, the bond energy is related to the attraction of the electrons to the neighboring nucleus. So let's say these two atoms that you see here at the top are trying to make a bond. If this distance between them is great, then that attraction, okay, is strong but not really fulfilled. So that's a high potential energy, right? There's a potential to draw them together. As they get drawn together, that potential energy is going to lower as the bond forms. Keep in mind that nature tends toward lower energy. So if it can lower the energy, that's what it's going to prefer. So these atoms would like to be closer together because that's where the potential energy is lower. So the key here, the potential energy of the electrons decreases as they approach the nucleus of another atom. So we can lower their potential energy by attracting them to a neighboring nucleus. As this occurs, as they move closer and closer and closer together and the energy is lowered, that energy's got to go somewhere. Right? We can't create or destroy energy. So if we're going to lower energy by bringing two atoms together, then where's the energy going to go? Energy is released during the formation of a bond because the energy decreases as they move closer together. Now, this may be different from what you hear in biology, so I want to make sure we're clear. When a bond is formed, that is when energy is released, because the electrons lower their energy in that attraction to the neighboring atom. So if we want to break a bond, what do you have to do? You have to put in energy. Breaking bonds, breaking anything. Think about if you want to break something, you got to put in energy, right? Now, you may get energy out if you form a new bond that is stronger. So in biology, when we're talking about the breaking down of ATP, etc., to release energy, the reason that breaking releases energy is only because it forms something stronger. So breaking always, always, always takes energy, and the formation is what releases. So if we can form something stronger than we broke, that's how we're going to get energy. So if we're talking about respiration in the body, what we're forming, that carbon dioxide and that water, there's strong bonds in there, and so that's how we release energy. Okay, if you need some more clarification on that. Biology and chemistry don't disagree here, it's just that biology is a simplification. But in chemistry, we want to talk specifics. When we break the bonds, you got to put energy in, but you may get it back if you can make some new bonds. So bond energy, the definition, is the amount of energy required to break the bond. But that would also be equal to the amount of energy released when that same bond forms. Okay, so keys here. Amount of energy required to break the bond. Also, amount of energy released when bond forms. Okay, so make sure you know that distinction. It doesn't require energy to form a bond, it requires energy to break a bond. And we release energy when we form the bond. For example, if you have hydrochloric acid, which is an HCl bond, and you want to break it back into hydrogen and chlorine, that's going to take 432 kilojoules of energy. We use positive signs when something is endothermic, meaning you've got to put energy in to make that happen. However, if you want to do the opposite, you want to take those two atoms and make a bond, then you can get that same energy back. And here, notice your sign change, negative sign, exothermic. So it requires, notice the language, that much energy to break the bond, and then that much energy is released when the bond is formed. Notice the per mole aspect in both of these values. So if you want to make 2 moles of this, twice as much. If you only want half a mole, then half as much, and so on and so forth. So this can become a conversion factor. And we'll see that as we move through the class. Alright, this is kind of a popular graph that shows us the energy change as a bond is formed. So over here on the right-hand side, you're looking at the atoms being far apart. And so the energy is just kind of medium. They're hanging out as 2 separate elements. As they get closer together, the electron on this one is attracted to the nucleus on that one, and vice versa. And that attraction lowers the energy. So it lowers, 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 until you get to this perfect low energy state. And at the valley, the lowest place, that is where there is a bond. So from this graph, we can say, okay, right here, if we go down to the x-axis, that's where the distance is located, then we can figure out what the bond length is. And if we go over to the y-axis, where the energy is, we can figure out what the bond energy is. Again, this would be the energy that you need if you want to break the bond, but the energy that you get if you make the bond. Now, what's going on over here past that point? So here's the perfect distance. You get them too close, though, and repulsion is going to occur because the nucleus of this one, which is positive, is getting too close to the nucleus of this one, which is also positive, and they're going to start repelling. So over here to your left, you have repulsion going on. On the left-hand side, as you move from the right-hand side, you have attractive forces that are lowering your energy, repulsion forces that are raising your energy, but right here in the middle, you have this perfect balance of attraction and repulsion, and that is where your bond forms. What are some factors that affect how strong this bond is? As the radius of your atoms gets bigger, the bond gets longer. So those atoms can't get as close together to form the bond. And because of that, if they can't get as close together, then they're going to have a lower bond energy, which means a weaker bond. So the key here, if you have atoms that are large, so the atomic radius increases, that's going to make your bond length increase and make your bond energy decrease, so your bond's weaker. The reason for this is if the nucleus is in close proximity to the shared electrons, that's a stronger force of attraction between the protons and those electrons. So that would be a stronger bond, a higher bond energy. But when the force of attraction is greater, because of these closer proximity, it's going to make the bond harder to break. So that's when the bond energy would go up if they were close together. But think about if a bond is really long, that's going to be easy to break that bond. So if the bond energy is low, that's because the atoms are kind of far apart. So we can just go in and break them apart really easily. But if they're tiny atoms and they pack in really, really tightly, it's going to be hard to break them apart. Here's some examples. So we have a carbon-chlorine bond, a carbon-bromine bond, and a carbon-iodine bond. Notice they're all single bonds. But the strongest of these bonds is the carbon-chlorine bond. And the weakest is the carbon-iodine bond. So why would this be? They all have carbon, they all have a halogen, but iodine is so much bigger than chlorine. If you look at the periodic table, you know the size increases as you go down. So iodine has more energy levels. We've got big iodine compared to small chlorine. So that bond is longer. You notice here in the bond length, it's longer. So it makes a lower bond energy or a weaker bond. Now let's look at these two. Which molecule here would have the least amount of potential energy, meaning the least bond energy, associated with its bond? Well, this bond right here compared to this bond. Remember, a bond is center to center. So because this black atom, whatever it is bigger, this bond length must be longer. So a longer bond length is going to mean a weaker bond. Now when it's talking about potential energy here, it's talking about that graph, right? So on the graph, we get closer and then we dip down and go up. So it's saying which one would be at the lowest potential energy. Well, these two, they can get closer together. So their dip is going to be lower. But if we think about these two, they're getting closer together. Oh, but that's the closest they can get, right? Because they're bigger atoms. So here, your potential energy isn't going to be as low. And so you're going to have less bond energy, right? Because your bond energy is dependent on the depth. So this one is a lot deeper in its potential energy, so it has a lot bigger bond energy. Okay, let's go back to that graph and visit that one more time. So in this graph, here's hydrogen-hydrogen, which is kind of what we're comparing it to. And let's say the other one is hydrogen-bromine. Well, it's still going to do the same thing, but they're not going to be able to get as close together. And then they're going to start repulsing. So their potential energy is just going to be like right here, whatever this is. Okay, maybe like -300, who knows. And then their bond length, if you go down, the bond length is going to be bigger, right? So they're further apart, and they're going to have less potential energy, and therefore a weaker or lower bond energy. All right? Another factor that we have to consider, though, is how many bonds there are. So if there's a single bond compared to a double bond, compared to a triple bond, that's going to make a difference in terms of the bond strength. So the number of bonds as it goes up, that's going to cause the bond length to go down, and therefore the bond will be stronger, or the bond energy will go up. Okay, so the keys here, as the number of bonds increases, the bond length decreases, the bond energy increases. But what is a bond? A bond is shared electrons. So let's say you're just sharing 2. Well, it might be like that. But if you share 4, well, that's going to draw you closer together because you're attracting more electrons in the center, pulling those protons in tighter from the nuclei. Well, what if you're sharing 6 in a triple bond? That's going to pull those nuclei in even tighter. So as the electron density between them increases, it's going to increase the attractive force of that nucleus, pulling those protons in, making those bonds stronger. So we go from the weakest bond being the single bond, the strongest bond being the double bond. Simply because it decreases the length, and if the length is lower, then the bond can be stronger. All right, for example, here we have fluorine compared to oxygen compared to nitrogen. Now, fluorine is a smaller atom, but it only has a single bond. Oxygen is a little bit bigger, but it has a double bond. So notice the bond length is less, actually, than fluorine, even though oxygen is bigger. And then nitrogen is even bigger than oxygen, but it has a triple bond. So that triple bond is going to pull those nitrogen in closer together. So nitrogen's bond energy is going to be way greater than the other two. So the number of bonds going up causes the bond energy to increase, the bond length to decrease, and then the potential energy, okay, if you're thinking about our graph, is going to dip down way lower if there's a triple bond. It's not going to dip down as much if there's a double bond. It's not going to dip down nearly as much if there's a single bond. So that low dip tells us that bond is really strong. Bond order is just another way to say how many bonds there are. So if there's like a single bond, that would be bond order 1. Double bond, bond order 2. Triple bond, bond order 3. I just want you to be familiar with that language because they'll use that on the AP exam for some odd reason. There's a simpler way to say that, but you just don't want to get confused by that. So if they say, what is the bond order? If it's a double bond, bond order 2. Okay. As the bond order increases, so if it's a double bond, for example, that bond order of 2 is going to be a shorter bond than a bond order of 1. The potential energy that's associated with that bond is going to go down, and then, of course, that's going to be a stronger bond. So your bond energy goes up. All right, here's an example. They're using different models here. So in I, they have a carbon-carbon triple bond, and they're showing that by these 3 lines in the ball and stick model. Think about if you like stuck these together using our model sets. That's kind of what they're showing you here. And then this one has a double bond. So this would be a bond order of 3 compared to a bond order of 2. So which one would have the lowest potential energy? Okay, so if we're thinking about our graph, which one would dip lower? Well, I would dip lower, right? Because it's a stronger bond. So as they come together, ooh, strong, strong, strong attractive forces causing that dip. So that would be stronger with the triple bond. And then which one would have the lowest bond energy? Well, bond energy is the energy required to break the bond. So which one's going to be easier to break? Well, duh, a double bond is easier to break than a triple bond. Okay, so when you see potential energy, you want to think how low is the dip. When you see bond energy, that's how hard is it to break. Lowest is what they ask for, so weakest bond. Okay, there's those explanations if you want to jot those down. Alright, just some vocabulary in terms of types of modeling. So there's a modeling you can do called space field modeling, and that's what we saw. I'm going to scroll back. That's what we saw back here on this slide. So what are some of the advantages of this model? So in a space field model, you can see the difference in the radius of the atoms, and you can kind of get an idea of the bond length. It doesn't really show you the 3D positioning of the atoms, and also we can't see the number of bonds in that space filling model. It just shows the atoms kind of literally stuck together. In a ball and stick model, which what we see here and what we see if we're going to build our own model sets, this has some advantages and disadvantages. So it shows you kind of the positioning of the atoms really well in the 3-dimensional space. You can get an idea of the bond angles. It'll show you very clearly what type of bond you have, single, double, or triple. But the problem is the balls and especially the sticks are not really proportional to the actual sizes. And so, for example, here, I'm going to flip back, but it looks like these bonds are all kind of the same length. But we know that a carbon-hydrogen bond is not going to be anywhere near the same length as a carbon-carbon bond. And also, if you look at the picture, the triple bond looks to be about the same size as the double bond. So it really doesn't do a good job of giving us an idea of size, and especially not the size of the bonds.